Good morning, everyone. I'm Weijing from the University of Chinese Academy of Science. It's my honor to introduce our work, Deduplication-Friendly Watermarking for Multimedia Data in Public Clouds. This was a joint work with Chen from the Michigan Tech, Limin from the Chinese Academy of Science, and Jiwu Jing from the University of Chinese Academy of Science. Firstly, let's get a quick start from the cloud storage and the deduplication. As we all know, the cloud storage service has been widely used in practice nowadays. The cloud client can store their data in cloud storage conveniently and economically, which is provided by various cloud storage service providers like Amazon, Microsoft Azure, iCloud, Google Drive, and AliCloud. To solve the ever-surging volume of data nowadays, the cloud service providers adopt deduplication techniques to maximize usage of their cloud storage space. The fundamental idea of deduplication is when two or more files stored in the cloud are identical, only one unique copy will be stored. Deduplication can be categorized as a server-side deduplication and a client-side deduplication, based on where the deduplication is performed. In the server-side deduplication, the client uploads their data to the cloud server, and the cloud server transparently detects and removes redundant data. In the client-side deduplication, the data owner will ask the cloud server whether the file has been stored before uploading. If not, the data owner outsources the file to the cloud server. Otherwise, the cloud server accepts this client as the data owner of the file after validating its ownership without requiring the data owner to upload the file again. This validation process is called proof of ownership, or POW. In this work, we focus on the client-side deduplication for its significant bandwidth and storage saving. According to the technical report from Cisco, about 34% of data outsourced by individuals are multimedia data, and 24% comes from the social network. Besides, most multimedia data and nearly all the data from the social network are stored in public clouds nowadays. So, considering large volume of multimedia data have been stored in public clouds, performing deduplication over them could be beneficial. By outsourcing multimedia data to the public clouds, the data owner may lose ownership of their files. A traditional remediation is through encryption, which may create an obstacle to data sharing and data processing. Fortunately, for signal-tolerant multimedia data, we have an alternative for ownership protection, which is through watermarking. Watermarking publicly shared multimedia data in public clouds is common nowadays. One typical scenario is crowdfunding projects in which data owners share the same multimedia file with others who they actually don't know. The data owners work together on the identical multimedia file outsourced to the public clouds like a community and are likely to maintain ownership of the file. Another scenario is the online teaching, which is boosting during coronavirus. The teachers may use the same multimedia files as teaching resources and upload them to the public clouds for sharing to their own students, while expect the ownership of these teaching resources can be well protected. Unfortunately, the traditional watermarking will disturb deduplication since, without watermarking, the deduplicated file can be easily detected and removed. But after introducing watermarking, the identical file will be processed to be different files by different data owners using their own secrets, and the different watermarked file cannot be duplicated anymore. So, how to deal with this conflict between duplication and watermarking? Okay, Before introducing our solution to address this problem, let's look at our system model and adversarial model first. We consider a system consisting of the data owner, the cloud server, and the data user. The data owner is fully trusted and outsources their watermarked multimedia data to the cloud storage. The cloud server offers storage service and performs deduplication. It's honest but curious, which means the cloud server will honestly respond to client and execute operations required by the data owners and data users. But it's curious about the original file underlying the watermark file uploaded by the data owners. The data user can use the file, but the malicious data user attempts to become the data owner. Besides, it's curious about the content of the original file belonging to data owners. The communication channel is assumed to be protected by SSL and TLS. Okay, I'm ready to present our solution now. Considering practicality, we don't rely on any trusted third party or interaction among data owners beforehand. So we adopt the convergent encryption, or what we call CE for short, in designing the watermarking. By performing CE, different data owners who possess identical files can obtain the same secret, which can be used to generate the watermark. But CE alone is vulnerable to the brute force attack. Imagine that the adversary guesses the file content in a brute force manner and derives watermarks to CE. By comparing to the watermarked file uploaded by data owners, the adversary can verify the correctness of its brute force guessing. So, to prevent this brute force attack, we separate the watermark into two independent components, the watermark location and the watermark content. The watermark locations are derived through CE. And the watermark content is a random bit string picked by the initial data owner, which will be stealthily propagated to other data owners via the untrusted cloud server. Our design is a watermarking in spatial domain, which is extensible to other watermarking schemes as well. To facilitate understanding of our design, we take grayscale image as an example in the follows. But note that our design is extensible to other types of multimedia files like color images and videos. To enable the client-side deduplication, the mentioned solution is still faced with the following issues. First, how to determine if the multimedia file has been stored in cloud. Second, how to allow the cloud server to validate ownership of the original file over the watermarked file. And third, how to propagate the random watermark bit string via the untrusted cloud server. For the first question, a straightforward solution is ask the data owner to compute and send the hash value of the original file to the cloud server for searching, which is vulnerable to the brute force attack and side channel attack. Instead, we use a hash value of public portion of the watermarked file. Since the watermark locations are derived through CE, the data owner always can exclude the watermark locations from the original file to obtain the public portion of the file. Then the data owner computes the hash value of the public portion of the file as a checksum to find out whether the file has been stored. In this manner, the adversary can at most obtain the public portion of the file through brute force attack. The original file is still protected by the random watermark bit string. Now we answer the second question. Remind that in the client-side deduplication, when the file has existed, the cloud server needs to validate the ownership of the following data owner. Such interactive protocol is called POW. The cloud server is trusted and has access to the original file. It will challenge the prover and verify the correctness of ownership proof returned by the prover, which is supposed to be computed from the original file. If the ownership proof is correct, the cloud server adds the prover to the owner list of the file. But the traditional POW cannot work here since, in our setting, the cloud server is untrusted and only has access to the watermarked file rather than the original file. So to allow the cloud server to check the ownership of the original file, we require the initial data owner to prepare a miniature of the original file to assist the cloud server. Such miniature need to be carefully designed to fulfill security and performance requirements. For security, first, it should be used to verify ownership correctly. Second, it should not leak any information about the original file. And lastly, it should be unique for different file blocks. For performance, the miniature should not incur any significant overhead. Therefore, the miniature, or what we call POW tag for each file block, is constructed like this. The verification coefficient will not be disclosed to the cloud server directly. Instead, modular exponential result will be sent to the cloud server. When another data owner, or what we call a prover, comes at this point, the cloud server challenges this prover with a set of index of file blocks and a set of temporary challenge values. The prover computes the mu like this and tail like this. The cloud server finally computes sigma and checks whether these equations hold or not. If so, the prover passes the ownership checking and will be accepted by the cloud server as a valid data owner. As for the third question, without any trusted third party and interaction among data owners beforehand, the data owners recruit the untrusted cloud server to propagate the watermark bitstring. A straightforward solution is the cloud server sends the watermarked file to the prover before checking its ownership, such that the watermark random bitstring can be easily extracted by comparing the original file and the watermarked file. However, this approach discloses too much information about the original file to the prover before POW and incurs significant communication overhead. So, is it possible to optimize this basic approach? The answer is yes. Based on nature of watermarks that are distributed sparsely across the file, we design a novel compression approach to process the watermarked file, which can be viewed as a two-dimensional pixel matrix to two much smaller matrices. The key insight of our compression approach is to divide the n times n matrix to several columns and rows and aggregate them together iteratively to derive a compressed column matrix and a compressed row matrix. The differences caused by embedding watermark bits will be recorded in the two matrices. In this manner, the communication overhead can be reduced significantly, and due to aggregation, the compressed matrix loses much effective information of the original file. It cannot be used solely, and it's difficult to be restored to the watermarked file, and hence the data disclosure can be mitigated. As for extracting the watermark bitstring, the prover first determines the watermark locations through CE. Then, the prover compresses the original file, follows our compression approach I've just introduced. Then, by comparing the compressed Chrome matrices of the watermark file and the original file, the prover can obtain the aggregated watermark bits in each row, and so as to the compressed row matrices of the watermark file and the original file to obtain the aggregated watermark bits in each column. Next, similar to the schedule game, by mapping back the aggregated watermark bits to the watermark locations in the original file, the watermark bit string can be extracted. For the watermark bits that cannot be determined using mapping, the prover will retrieve elements in the watermark file directly from the cloud server. Okay, I have already presented all the key insights of our work. In the following, I will analyze the security of our DEW. We have proved that the cloud server and the malicious data user cannot obtain the original file. Besides, the malicious data owners cannot pass the POW check. More details are available in our paper. Okay, next, I will present performance evaluations phase by phase. In the initial upload phase, as shown in the figure A, the watermarking computation is mainly determined by the length of watermarks rather than the file size. And as shown in the figure B, first, for fixed block and symbol size, the computational cost for generating POW text increased linearly with the file size and decreased with the symbol size, while it's independent to the block size. From the figure C, when given fixed block and symbol size, the time for computing public verification parameters is associated to system parameters, which is independent to the file size. In the client-side deprecation phase, from this figure A, we have the following observations. First, the time for generating POW proof increased linearly to the file size but keep consistent when reaching a threshold. This is because, for performance purpose, when the number of file blocks in a file is no more than 460, the cloud server will run POW protocol by checking the entire file. Otherwise, the file blocks being checked is 460, which is shown by the previous work to be able to efficiently detect slight corruption of the file with a high probability. And second, after reaching this threshold, for a fixed symbol size, the computational cost for POW proof generation grows along the block size. We can know the time for verifying the POW proof from figure B that for the fixed blocks and symbol size, the time cost is constant. Additionally, the time cost increases with the block size and decreases along the symbol size. The compression time is depicted in the figure C, which is mainly depends on the file size. And as shown in the figure D, when the file size is fixed, the time for extracting watermark bit string grows linearly with the watermark length. In addition, for fixed length of watermark, the computational overhead for extracting watermark bit string grows along the file size, since extracting process requires retrieving the entire file. To evaluate the effectiveness of our compression approach, we define a compression rate rule here. The experimental results are recorded in the table 1. From the table, we can observe that the compression approach can save at least 84.4% bandwidth compared to transmitting the original file entirely. In conclusion, in this work, we are the first to identify a fundamental conflict in deduplication-based cloud storage systems that the cloud service providers want to remove duplicate data to save storage space, while the data owners want to protect their ownership of their outsourced multimedia data by embedding watermarks, which may hinder deduplication. We designed a deduplication-friendly watermarking scheme that can resolve the aforementioned conflict. A silent feature of our design is it doesn't require any interaction among data owners as well as any trusted third party. Security analysis and experimental evaluation show our DW is secure at the cost of modest additional overhead. Thanks for listening, and please feel free to ask questions about our work.